So the next addressing mode that we would discuss is called indirect addressing mode. This is very popular, especially with things like pointers. Imagine, like we have learned about pointers in C programming language, right? So imagine you have some pointer based arithmetic or pointer based operations in a high level language like C. To translate that pointers based statement in C programming language to machine level language, it's very useful if you have indirect addressing mode as part of your addressing modes. So within indirect addressing mode itself, there are two broad subcategories. One of them is called register indirect addressing mode. The other is called as memory indirect addressing mode, right? First, let's look at register indirect addressing mode. Again, the concept here is very simple. The concept here says, imagine if I have an instruction like this. What does this instruction do? That's very important, right? Look at this. I have my, so if you notice, I have my, so here this part is my standard register addressing mode. This is my register addressing mode. Here this is register indirect addressing mode. This is register indirect addressing mode. And the way we can differentiate is because of this symbol at, right? This at is something that we use to implicitly mention that what we are doing here is a indirect addressing mode. Of course, indirect addressing mode with a register, hence it is register indirect addressing mode. So the way it works is, look at this. If I have an address like this, okay, what does this do first of all? Okay, let's go here. So this is my register file. Look at this. This is my register file which consists of all the registers. So what I do now is I go to R0. So let's assume this is my R0. So I go to R0. R0 will have some value stored here. R0 will have some value stored here, right? The value stored within R0. So let me write it differently. So R0 contains the effective address in the memory, right? So to fill this value, so add whatever is stored in the address that is there in your register R0. So this basically means whatever is this address, whatever is the value that is there in R0, that's the effective address or the actual address of whatever we want to place here. So let's assume this is, let's assume this is some location 2080. Suppose the value that is stored here, the value that is stored within R0 is, let's say, 2080. Then we go to the memory. Again, this is my main memory. This is my main memory. I go to this memory location 2080. Whatever data is here, look at this, whatever data is here. Okay, this data I will take it. I will add it to whatever data is there in register R1. And the final result, I'll again store it in this location. Okay, so the way it will work is, so look at R0. What is the value stored in R0, right? So that value that is stored in R0, let's assume R0 contains 2080. The data stored in this memory location, we know that the squared braces, right? These squared braces here mean the data stored in this memory location, right? What is the memory location? Memory location is the value of R0 itself. That's very, very important, right? So it is the value stored at R0, that is the effective address. So this 2080, so let me write this actually more precisely so that there is no confusion. So whatever is data stored in memory location 2080, add it to whatever is stored in register R1 and store it finally to memory location 2080. Why are we using 2080? Because R0 here contains this. That's very, very important, right? So to actually obtain this value, first we have to do one register reference because we have to get what is the value stored here, which is 2080. Then we use this to do one memory reference. Look at this, there are multiple references that are happening here. The first reference here is a register reference here. There is a register reference that is happening. Then there is a memory reference that is happening. From the memory reference, whatever data is here, we get that data. Now again, there is another register reference that's happening because I need to read this value. I need to read this value. Right here, there is a read here. There is a read here. There is a read from register R1. Then we perform the arithmetic operation of addition, right? And then the final result, we are again storing it here. The final result, we are again storing it here. Again, to store the final result will be stored in the address that is in R0, which means we again do a register reference, a memory reference, and store it here. Okay, that's how the flow actually works here. So this is called register indirect because the address of the final memory location where the data resides is in a register. Very simple. This is how pointers work, right? How do pointers work? A pointer contains the address of a value, right? A pointer. So if this is a pointer, the pointer contains the address of something. So here you can think of this as a pointer because this contains your R0. You can think of it as a pointer because R0 contains the address of the actual memory location on which you want to perform operations, right? So again, whenever in any programming language that have pointers, or if you know Java or other programming languages where there is something called as references instead of pointers, indirect addressing mode is extremely useful if you have it as part of your microprocessor architecture. Now look at this. The second variant is memory indirect addressing mode. So how does the memory indirect addressing mode work? Very similar to register indirect addressing mode, except that here look at this ampersand 2080. So this is in register reference now. This is register reference. This is memory indirect addressing mode, right? This is your register addressing mode. This is your register addressing mode. Now how does this work? What happens here? So what happens here is the moment it looks at this, there is ampersand 2080. So it goes to main memory, right? So the control unit basically goes to main memory, goes to location 2080. Suppose within 2080, let's assume there is 4000 here. So it goes to address 4000 now. It goes to address 4000 now. It goes to address 4000. Here lies my data. So this is what will be used here. So if you want to think about it, the way it will work here is the memory value stored at 4000 will be equal to the memory value stored at 4000 plus whatever is the data stored in register R1. This is how this will translate to. But again, look at this. First, what are the references that are happening? There is one reference that is happening. There is one memory reference to go here. There is one memory reference to go to memory location 2080. There is another memory location. There is one more read. So there is a read that is happening here. Then using this value, I again go to memory location 4000. Again, I perform a read here. So this will give me this value now, right? Then to get this value, I'm doing one more read, one more register read. One register read. Here we are doing one memory read. Here we are doing one memory read, or one memory reference, if you want to call it so. Finally, I'll have to again write it here. Again, to write it here, it says ampersand 2080. So again, I go to 2080 location. I look at what is the address here. In that address location, I'll write the resultant of this whole arithmetic operation. This is called memory indirect addressing mode, right? Because we are using a memory address like this. We are using a memory address like this to store the address of, again, this is your effective address here. This is your effective address. What is effective address? Effective address is the actual address where the actual final data resides that you want to use, right? So it's 4000. Again, I'm highlighting here. This is the actual location where the final data resides that you want to access and process, right? Very simple concept here. These are called as indirect addressing modes. Remember, indirect basically means pointers. That's how I remember this. Within indirect, my pointer could be stored in a register or in a memory location. That doesn't matter. Very simple concept here, right? This is very, very popular in most modern microprocessors. It's very useful when you have programming languages like C, Java, Python, etc., which have pointers or some type of pointers. C has explicit pointers. Java, everything has something called as references. Okay, if you know Java. If you don't know Java, don't worry about it. Okay. The next concept is called as indexed addressing modes. Again, arrays is a very, very important data structure, right? In most programming languages, right? Imagine if I create an array A in C programming language, it starts with index 0. This is called indexed addressing mode because arrays are always indexed. So I start with address 0, 1, 2, up to n-1, and I have an index I here, right? So we'll use the C-based 0 indexed arrays just for simplicity. Okay, now let's see how it actually works. Imagine if I have again, this is how an instruction will look like. It says move to register R1. So here what do you have? You have register addressing mode. This whole thing is what is called as your indexed addressing mode. Remember, very importantly, in arrays, you can randomly access any of these indices, right? You can randomly access data at You can randomly access data at any index at any point. So if you want data stored at index I, you just say AI in C programming language, right? This is how you refer to it. Now, whenever you write AI, the way it gets translated. So suppose, imagine if you write AI, right? So how does it get translated? So A as an array itself has something called as a base address. There is something called as a base address. Again, this is a concept that we have learned when we learned C programming language and when we learned about how pointer arithmetic itself works. Base address is nothing but the address of, this is your base address. Base address is the location where your array is stored in C programming language, where the 0th index element starts. This address, literally this address is your base address, where everything starts being stored. So that's what we refer to here as BX, base address, right? So to store base address, most modern microprocessors have something called as base address register, right? So they have something called as base address register. Similarly, there is an index. So I give a base address and I give an index, very simply put, right? So what happens here, this index, suppose if I say AI, my address, this base address is the address of A0, right? That's what is your base address. Your index here is nothing but I. Your index is I, your base address is the address of A0. Now when you have both of them, again, in some microprocessors, your IDX or index itself is stored in a register called as index register. In some microprocessors. Okay, so how does this work now? How do you get the effective address in this case? Again, it's very, very simple. So what we do now is whatever is stored in the base register, whatever value is stored in the base register, which is nothing but your base address, and whatever is stored in the index register, right? Whatever is stored in the index register, we first perform a simple operation. We first perform the operation of addition. Because to locate AI, I need to add the base register to the index, to the value that is stored in the index, right? The index stores how far away. For example, again, this depends on whether we are storing in the case of C programming language, this depends on whether we are storing integers, characters, floats, etc. All that part the microprocessor doesn't care about. That's taken care by the compiler, right? So I have the index register. What I simply do here is I add both of them. I get a resultant. This addition actually happens within the arithmetic logic unit. So first I read the base register. This is one read. So let me also highlight them, right? So there is one read here, one memory reference to the base register, one read to read the index register. Then I add both of them. I get the arithmetic logic unit here. Using the arithmetic logic unit, I get the address. This address is now my effective address. This address now is my effective address. So using this effective address, now I go to the main memory. I go to the location of the effective address. Now here lies my data. So here what am I doing here? I'm doing one memory read here. This whole thing gets replaced by whatever is stored here. So what will happen here in this case is R1 becomes the value stored in R1 plus, let's assume some number is stored here. Okay, whatever is stored here. So I'll just place it like this. Okay, so whatever is stored here goes here, right? So this is extremely useful when you want to randomly access any element of your array. This is extremely useful, right? If I want to access the ith element of my array, what do? I just say AI, right? I just say AI. So then the base address of A is used. The index of the ith index is used here. They both are added, and to add them we need to read once from the base register, we need to read once from the index register, perform the addition as part using your arithmetic logic unit, get the effective address. The effective address now tells me where I have to go in the main memory. From here I'll perform one read. Very cool. Again, to read this value, so there is one, so here what all do you have? You have two register reads and one memory read. Here what do you have? You have one register read here. Finally, you have a write to the register. This is how indexed addressing modes actually work. Very simple concept. Remember, here we want to again, I'm using this very, very carefully. Here we want to randomly access any element in the array, right? And this is how actually most array-based instructions in your C programming language get translated to machine level language. Again, we have explained this when we learnt C programming language, but we did not know how it will actually translate in terms of the low-level computer organization itself. The beauty of learning computer science is what you learned in your first year BTech, your C programming language, is connected to computer organization. Most likely you learn this in your second year. This is connected to compiler design. This is connected to operating systems. Again, some of these things are also connected to your computer networks. So what you learn in your first year is deeply intertwined to lot of topics that you learn throughout your 4-year undergraduate studies and your 50-year career after that, right? So that's very, very important. Okay, so this is called as indexed addressing mode. So there is something slightly different called as indirect indexed addressing mode. Okay, so this is often referred to as direct indexed addressing mode. There is a small variation to this called as indirect indexed addressing mode. See, the moment you have indirect, just think of it like pointers. Okay, let's see how this works. Suppose I have an opcode and I have an address which uses this mode. This uses indirect indexed addressing mode. The moment, first of all, it's an indexed addressing mode, which means I'll take my data from the base register, the base address. I'll also take the index value from the index register. Now I add both of them using my ALU. What it gives me is some memory location. Okay, I got some memory location, but it is indirect indexed addressing mode. So indirect basically means here that whatever I have in the memory location is not the data, it is the effective address. Now I need, so this is the indirect part. This is the indirect part. This whole thing is your indexed part. This whole thing is your indexed part, right? So imagine if I have an array now. Imagine if I have an array. Imagine, so indirect indexed addressing mode basically means, imagine if I have an array, right? So 0, 1, 2, 3, so on, so forth, some location I, so on, so forth, right? In this address, so if I use this, right? So what is this now? This is nothing but this location, right? This is stored in memory, right? This whole thing is stored in memory. So in here, what do you have? In here, you have a pointer. In here, what you have here is a pointer. So you have an array of pointers here. You literally have an array of pointers, because what does my AI contain? What is this? This memory location is nothing but my AI. What does AI contain? AI contains an address, which means AI contains a pointer, which means what we have here is an array of pointers. Again, array of pointers is a topic that we have discussed extensively when we learned about C programming language, right? So if you want to go back and read that, please go ahead, right? But effectively what's happening is my data here, so what you have here is an array of pointers, right? So when I perform all this base address plus index, add both of them and go to the memory, what I get is the effective address. Here lies the address of the data that I want to access, which means this is the pointer now. Very simple logic, right? So oftentimes this is also called as direct indexed addressing mode, or this is simply called indexed addressing mode, right? Both indexed addressing mode and indirect addressing mode can enable us to have random access. The reason I'm pointing to this is because the next mode that we will learn does not have this. Okay, so let me discuss this. Okay, there is something called as auto indexed addressing mode. Very interesting mode again. So here the way it works is this. Very interesting. Let me explain this. In here you can only linearly access one element after the other element. You can't randomly access. You can't randomly access any element like in an array. So what you have here is a linear array element. It's a linear array of elements, but you only have linear access, not random access. The way it will work is this. Again, there are two types of auto-indexed addressing modes, auto-increment and auto-decrement. I'll come to this in a little while. But first let's understand. Imagine if I have an opcode and I have an address. Let's assume this address is an auto-indexed addressing mode. See, look at this. It is indexed, but there is auto here. What does this auto basically mean? So this address, look at this. In the previous example, this address component had the base address and the index, two parts to it. It had two parts here, right? If you look at this, this address has both base address and index. It has two subparts in the case of indirect indexed as well as direct indexed addressing modes. In the case of auto indexed addressing mode, there is only one address. This address consists of the base address. There is nothing else. This address only consists of the base address. There is no index field. There is no index value. or there is no need of index register here. The base address is there. Then you have a constant called as step size. You have a constant called as step size, right? This base address is obviously stored in the base register. This base address itself is stored in the base register. Okay. So what this instruction does is whatever data is stored in the base address, right? It increments or decrements. It basically adds this constant. Remember, this constant is not coming from an indexed value. This constant is not coming from an indexed value. So the moment you have this base register, it simply adds or subtracts this constant value, which will generate the effective address. Then I go to this memory location and I get it. It is called as auto increment if we add the step size. It is called as auto decrement if we subtract the step size. Very simple concept here. Very, very simple. So there is no index field here. So because there is no index field, what can I do? Suppose imagine if I have a linear array. Okay, suppose imagine if I have a linear array, 0th element, first element, second element, third element, so on and so forth. My base address is here. My base address, which is the address of the 0th element, is stored in the base register. To this, first I'll add the step size. So first I'll access this, done. Then I'll access, by adding 1, I can access first element. Then I'll add 1 again. I'll get the second element. I'll add 1 again. I can get the third element. I'll add 1 again. I get the fourth element, so on and so forth. So there is only linear access. You can't directly jump to the ith element here. That's not allowed, right? Because there is no index field or index value as part of your address here. You can only go by incrementing it. You go from 0 to 1 to 3 or 4. By auto decrement, you go backwards. You can go from 4, 3 to 1. Right, so the auto index addressing mode itself can be auto increment, which means here in the ALU, as part of the ALU, you have the plus operation, or it could be auto decrement, which means you have the subtraction operation here in the ALU. Now, when you add base address to the constant step size could be stored in one of the registers. This is a constant value. This does not get changed, right? So now you add both of them and you get an effective address. And whatever your data actually resides here, right? This is also indexed. Remember, this is also an indexed addressing mode. Remember, it's also indexed because you can have a linear array like this being addressed using this, but it is auto indexed, which means it automatically goes from one location to other location. You can't randomly go to the ith location. You can only go from one location to the other location in a linear fashion. That's very, very important here. So here, very, very importantly, after the base address is updated, look at this. So suppose I have base address as 2080. Let's just say my base address is stored in some base register or some user general purpose register, and let's assume the value is 2080. To that, let's assume my step size is 2 bytes. Okay, this base address is 2080. Now what is the final resultant here? 2082. So what I do here is I go to address 2082 to get the actual data that I want. But this 2082 is also updated in the base address. Now the base address also becomes 2082 because the output of the ALU again goes into the base address itself. The base address gets updated because look at this, if it doesn't get updated, everything falls away, right? So imagine this address is 2080. Everything falls apart otherwise. Let's assume this address is 2080. Okay. Then let's assume my step size is 2 bytes. So first time what happens? I will go and access this 2082. Now I need to store this 2082 in the base address because the next time I auto increment, I need to get 2084. If I don't update this base address to 2082, if I just leave it at 2080, next time I'll again access the first element only. So what happens is the output of the ALU itself goes back and updates the base register that we have, right? Very simple. Again, increment basically means you're adding the step size. Decrement basically means you're subtracting the step size. That's it. The step size itself is a constant. Okay. Now within auto increment and auto decrement, there are two types, very simply put. There is something called as pre-auto increment and post-auto increment. Similarly for decrement also, there is pre-auto decrement and post-auto decrement. Let's look at a simple command to understand this. So let's look at this command. What does this say? So again, how do we show auto increment type of systems? This is the syntax. This is how we show it. Okay, so move R0, this is a register reference. This is a register reference. This reference basically says plus basically here represents increment. You're doing it before, which means pre-increment. Whatever value was there in R0, first pre-increment it and then use this. That's what is called pre-increment. Okay, this is like your x plus plus versus plus plus x in C programming language, right? This is your post increment. This is your pre-increment in C programming language. Similar notation here. This plus here basically means it's an increment. This plus with the braces means it's an auto increment addressing mode. And where is my base address? My base address is in register R1. Okay, that's what this means. That's what this means. So what does this do? It takes the data that is there in R0. It goes to my base address, gets the data from my base address. Let's assume my base address consists of 2080. Let's assume my R1 consists of 2080, which is my base address. And let's assume the step size. And let's assume the step size is 2 bytes. So what does it do? First, it's pre-increments. 2080 plus 2. 2082 is what I get. Now I go to memory location 2082, get the value, and whatever value is there, I move it into my register R0. This is pre-incrementing. Some systems can have post-increment, which means first I will use whatever is there in R1, then I will increment it, because probably it was already incremented earlier. First I will use this. This is exactly like your post increment and pre-increment in C programming language. Similar notation. First you use R1, then you increment it. Here you first increment it and then use R1. Similarly, you have your pre-auto decrement and post-auto decrement. Very similar concepts here, right? Most microprocessors either use pre-auto increment or post-auto increment. There's no point using both, right? But microprocessors can choose to have any one of them. And remember, please understand that in the auto-indexed or auto-incremented addressing modes, you can only move in a linear fashion. You cannot access these linear elements or linear array of elements in random fashion. The way you can do it in proper indexed addressing modes or in indirect indexed addressing modes. You can't do that here. That's very, very important. You can, because this base address is going to be constantly being incremented or decremented by the step size, right? Which means you can only go in this direction or in this direction. You can't directly jump to the ith location. That's very, very important aspect of auto-indexed addressing modes. Now we'll solve a bunch of problems in the next video.